All right, in this section, we're going to study a different way of studying probabilities, and it's via the normal distribution. And to kind of motivate this, I want to do an example. Let's flip a coin. Three times. So we can have anywhere from 0 to 3 heads. What I want to do is make a probability distribution table for this. So x can be anything from 1, 0, 1, 2, or 3. X equals the number of heads. So that's what I'm going to keep track of here. Now, the probability that x equals 0 means that we would have had to have 3 tails. That means the first would have been tails, the second one would have been tails, and the third one would have been tails. So we have tails, tails, tails. Well, the probability of any one flip being tails is 1 out of 2. So I'm using the independence of the individual flips to multiply these 3 things together. That gives me 1/8. You can put 1/8 over here, or you can put 0.125. Now you should realize that x equals 3 will give me the exact same answer, because 0 heads is the same as 3 tails, or 3 heads is the same as 0 tails, and tails and heads work exactly the same way. So in between these two, we have, I'm using 1/8 for this part, 1/8 for this part. We know the whole thing has to add up to 1, which is 8 over 8. I'm already using 2/8 for these things. That means what's left in the 2 middle places is 6/8. And in fact, x equals 1 and x equals 2 will have exactly the same probability, because 1 heads is the same as 2 tails. And 2 tails gives you the same values as 2 heads. 1 head gives you the same value as 2 tails. It's because it's so symmetric that we're going to get this. The 6/8 I'm going to split evenly up into 3/8 and 3/8. Now I'm going to go into Desmos and do a little graphing. I want you to see what happens when we flip more and more times. So let me put in here my table. I'll do the decimals. And you can see over here, it's graphing them. Let me show you what happens. So this time we're going to go, if you keep hitting enter, just go up to 10. Now, if you're doing this, if you're actually trying to do this along with me, I happen to know the formula for this. So most people, I'm not expecting you to know the formula. I just want you to see what the graph looks like when I do this. So ignore the numbers I put in. They're not important. Just know that I'm flipping a coin 10 times and I'm keeping track of the total number of heads. So here I finished graphing them. As you can see, what's starting to appear here is a bell curve. And that's exactly what happens. The normal distribution is a bell curve. So if you were to continue this for a mathematically infinity amount of time, this would be a perfectly good-looking bell curve. So the nature of this video is to get a handle on the bell curve. Let me come back to the picture for just a second. Underneath these, if I had made these blocks, or what do you call those, bar chart, if I had made a bar chart of that, underneath this curve would hold exactly 100% of the data. So when I draw my picture, this is typically what I'll make it look like. I'll typically draw some sort of a horizontal line best I can, and then a bell curve. It doesn't need to be that great. We just need to know some things about it. The first thing you'll notice is I didn't make it touch the x-axis. In fact, they don't even call it an x-axis. They call it a z-axis. And the top of this hump is right over the center, which is 0. And they'll tell you a couple things about this. They'll tell you that the mean equals 0, so that number there is the mean. And that they'll tell you the standard deviation is 1. We don't need to know much about the standard deviation just yet, but I will explain how sigma equals 1 encompasses the data. So I'll draw roughly the same thing again, 0. If I go out to 1 and back -1, so I'm going left 1 standard deviation and I'm going right 1 standard deviation. If I draw vertical lines so that I intersect here, the area of that shaded region is about 68%. In fact, let me go ahead and erase this piece in here. Now, as a decimal, that's 0.68. One of the things you should know that under the curve itself, the total area under this curve is 1. Otherwise, 100%. So 100% of the data is in this curve. These ends do not touch. They actually get closer and closer to the z-axis as you go farther out to the right or to the left, but they never touch. It's one of those mathematical things where it gets infinitely close but never actually touches. That is not a big deal to us, other than the fact is as you go farther and farther out, the numbers become very much less significant. If I go not 1 standard deviation, but out 2 standard deviations, and do the same thing I did before, it should be more symmetric than the way I'm making it look, so I'm going to try to make it look better. They should really strike at about the same place, so if I were to make this accurate, I guess this would be the 2 here. So let me take these things out. Then the area inside of this, between those 2 places, is about 95%. And if you were to go out another space after that, you're almost at 98%, actually over 99% of the data if you go out to -3 and +3. So we'll rarely have to venture that far out, because by the time you get past 3 or lower than -3, this curve is so close to the x-axis that the numbers are below any kind of accuracy we're keeping anyways. So we're going to play with this curve. What I hope to get you to notice is that there's all sorts of symmetry to this thing. Even though I may not be drawing it, you have to imagine it's a perfectly good-looking bell curve. So if I split it down the middle, 50% of the data is on the left, 50% of the data is on the right. If I have an area that goes from some negative number to the left, then the area in this piece, the reflection, if you will, through the 0 line, the reflection over here, this area over here is the same. So these 2 areas are exactly the same. What we're going to do is come up with some values for these areas, and we have a table that will help us do that. So let me pull up the table. The table is located in Blackboard. You should have a copy of it printed out for yourself, but here it is. This is the standard normal distribution table. And I'll tell you what this means in a minute, the various area to the left of the z-score. We'll talk about that in a minute. But you see the lowest z value they do is negative 3.9. So these take care of the negative value. So all of these are on the left of 0. And then on the other side, you have all the ones that go from 0. And they only go up to 3.9 because by the time you get to 3.9, let me go back here. Look how tiny these numbers are. And this, when they say the area to the left, let me tell you what that means. So I'm going to take a picture. I'm going to take one of these and make it small enough so I can fit it into our work. What I want you to notice here is the area to the left of the z-score. So what they're doing here is the following. So if you look up a negative number over here, what this table is going to give you is the area of the piece from negative infinity up to that particular value. So as a quick example of this, let me do one real fast. Let me do one at negative 1.0. So you come over to this table and you look at negative 1.0. You see it here about where my mouse pointer is at. I'll put my thing around. Negative 1.0. Now what you also do is look at the top of the page. What these are is these are filling out the decimal. So if you look at negative 1.0, this first number here is the area to the left of negative 1.00. Then if you go further to this next one, that would be if the number were at negative 1.01, negative 1.02, negative 1.03. On the other hand, if you were to go to negative 1.1, then this first slot represents negative 1.10, negative 1.11. So this on the vertical gives you one decimal place, and the rest of these numbers give you the second decimal place. So what I wanted was right into this spot here. You should have the table handy with you so you can see that right next to negative 1.0, we had 0.15866. That's the area of that piece. That's the way the table is designed. Let me come over to the table here. It might be easier to see it if I can expand here. Well, not that much. Right here's our guy. Negative 1.00 gives us the 0.15866. Now, on the other hand, you may be given a different style of problem. So to go from negative infinity up to that z value, I'll use the other side of the paper, the one that deals with the positive values. So this time I want 1.0. Here we are, 0.84134. And let me go ahead and put a picture of the table up there so you can see where it came from. The first spot, that means I'm in spot 1.00. Now, on the other hand, we're going to have a much different shadings than just going to the left. We can have them going to the right. We can have them in between two things. So let's look at a few of those and how you navigate around it. Let's start with this one here. I'm going to, this be 0. Now the table is not built to give you the area to the right. It only works towards the left. But this has, when I say has, the same area, I'm talking about the shaded region. So this is going to have the same area as this region that I'm going to draw next. It may not look perfect, but this area from -1 off to negative infinity is the same as the area from 1 to infinity. This is because the graphs are so symmetric. They may not look extremely symmetric based on the way I draw them, but believe me, they're completely symmetric. So anytime we have an area going off to the right, we can simply calculate this, which I think we even did earlier. We did 0.15866. So this area is 0.15866. Also keep in mind, many times the scores are given in terms, and they call this a z-score, by the way, not that. The numbers along the horizontal axis are called z-values or z-scores. This area may also be given as a percentage, so be prepared to work with 15.866%. So my efforts then is I am going to do a couple of examples. I'm going to leave you one, and I'll only leave the answers so that you can work it yourself. I don't want to work all of these for you. So for the next little while, I want to calculate the area of the shaded region. Maybe more than one. Let's start with here, -1.48. And then I'm going off to the left. So I come to my table. So I need to go back to the other kind. And I think I'm going to make this smaller while I'm here. So I need -1.48. So I'm going to be in the -1.4 row. I don't know how big I can make this before it runs off the screen. Let's see here. I have -1.40, 1, 2, 3, 4, 5, 6, 7, 8. So 0.06944. I wonder if it'll let me copy that there. And there we go. That's the area of the shaded region. Let's try -2.03. So here we are, -2.0, 0, 0, 0, 1, 0, 2, 0, 3. So that is zero. So that number there, 0.02188. Let me copy it. And that is the area of that shaded region. I just see I didn't put zeros on any of these. I usually do so that I know that I'm dealing with the standard normal distribution. We'll do things to these graphs to change some of these numbers. So it's important to put the 0 there so you know what you're dealing with. Now in this situation, let me put, let's try negative 0.94. This one I'll leave for you. The area that I get for that piece is 0.17361. Now let's move to the other side. So for this, we are going to have look up 1.5 in the table. So I'm going to be positive this time. So let me go to the positive side. And I want 1.50. I went a little too far on that. There it is at the top of my screen. So 1.50 is that number right there. So as we see that that's more than 93% of the data is in that shaded region. Oh, by the way, if I do this, it shouldn't take you much effort to see that that's going to be 50% of the data. Same on the other side, it's 50% as well. Let's try 0.07. Come down to the table, scroll up. 0.07, I got to go way over here. So there's 0.0. Oh, we can see the 7 up here. There's our guy, 0.07. And then let me leave one for you to make sure that you're catching on. This one had an area of 0.879. Now, if you have a problem like this, it's going off to the right. Remember the symmetry. This thing here has the same area through the symmetry. It'll have the same area as if you go and do the area to the left of negative 2.74. The reason why that's good is because I can use the table. Now I will go to the negative side of it, and let me get myself started with negative 2.7, 0, 1, 2, 3, 4. So that area is a little, that's 0.3%, a little more than 0.3%. So you can see the tail ends like that get really tiny. $1.09. Once again, you're going to look at making it go off to the left instead of to the right. So you're going to be looking over at negative 1.09 and looking at how much area is in there. Using the table, I'm in the negatives, so negative 1.0, 9 is going to be the very last one. Let me just make sure I didn't miss anything. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's our guy there at the end. So that's a little under 14% of the data. Now let me give you one to try. I'll just put the answer and you can check it on your own. The area I got for that one is a little, about 3.7%. So we've taken care of the most basic of the shapes. Now we need more complicated ones because this won't handle all the situations we're given. Another thing that can happen involves area between two numbers. So let me say on the left I have negative 1.4, but on the right, let's say I have 0.9. And I'm looking for the area in between here. So what we can do is we notice that the whole thing is 100%. What we do is we find the area of this white piece and we find the area of this white piece, and then we subtract it from 1. That'll give us the area that's left over. The reason why is since the whole area between here is equal to 1, I can take 1 minus this white piece minus this white piece, and I'll be left with the shade. So this one here I can directly do from the table itself. All I have to do is look up negative 1.4. There it is, 0.08706. That gives us that area. This area here, now remember our symmetry. I can actually go on the table and look up negative 0.9 to give me this area inside of here. So that's what I'm going to do, negative 0.9. Negative 0.9 is right here. So the area that's left in between here, to get this stuff, I'm going to take 1 minus 0.08076 minus 0.18406. I'll just use a regular calculator to make this happen. So there's the area that's left over. That is the area that's inside of the shaded region. Once again, I can directly use the table to get this little piece over here. I simply look up negative 2.14 in the table. And here's negative 2.1, 0, 1, 2, 3, 4. There's our guy. And then over here, I should be able to look up negative 0.3 or negative 0.03 and get this piece over here. It should be around 50%, you would think. Here we are, negative 0.00123. That's at 48803. And the area trapped in between, I'll put it over here, 1 minus 0.01618 minus 0.48803. So that area there, of course, is the area of our shaded region. Let me leave you one. Here, let's have both of them on one side. So this time, how do I do this? Well, this I can actually look up directly from the table, but on the positive side this time. So this number in here is going to be more than 50%. I can tell that. So let me go to the table and look up 0.53. 0.50123. There it is. Now to get this little piece here, I can look up negative 1.32 in the table. Negative 1.3012, that guy there. That is that area inside of there. To get our region in here, I do the same thing as I have all the other ones. 1 minus 0.70194 minus 0.09342. And that is our area that corresponds to the in-between part. Keep in mind too, visually, these should look about what they end up being. Obviously, if you go past 0, this white area should be greater than 50%. The reason I mention that is if you come up with a number that doesn't seem to match the physical size of the shaded region or the white region, you need to keep on your toes about that. Chances are you probably looked something up incorrectly in the table. These can help you keep right answers. Let me give you one try. I think I meant to give you that one to try, but then I went and ended up doing it myself. I'm going to give you one more. There's the area of that region there. Now what we've done so far in all of these pictures is we've done one thing. We've read the table in one direction. There is an alternative direction that you need to be able to read, and that depends on the shaded region again, but you're going to use the table in the reverse to what we did before. What will happen is you'll know the area, but then you'll have to go back and figure out what the z-score was. So let's come and try an example or two with that. I'll show you how it works. All right, suppose you are not told this, so this z value you do not know. However, you're told that the shaded region has a certain area to it. So let's say the shaded region is, I don't know, let's call it 20%. So we'll say 0.20. That's my shaded region. Now I come into the table and I'm not actually looking at these margins anymore. Now I'm looking inside of the table. I want to get as close to 0.2 inside of this table that I can get. So if you look here, I am seeing right about here, if you look at these two things, I think I can make a mark here. I didn't mean to do those two right there. This is very close. 0.2 is in between those two. What should you use for your value? So let's see where we're at. Negative 0.8012 2, 3, 4, 5. So it's between 4 and 5.2. Which do we use? Well, that depends on your instructor. In my case, I really don't care if you use either one of these. What I typically do will put an extra decimal, a 5. So like here we have negative 0.80123 0.834. Let me pull that up. All right, so what I've tried to do is make it so you can see everything at once here on the table. This here is negative 0.84, and this is negative 0.85. 0.2 is clearly in between those two values. This guy right here has got to be inside of those. That means it can't be exactly equal to negative 0.84, and it can't be exactly equal to negative 0.85. What statisticians typically will do was we will say that the z-score, let me put it over here, the z that they will use will be negative 0.84, and then they'll put an extra decimal. This way, this number is between these two. It's halfway between 4 and 5. So this is something that you can use, and that's how you go and get your z value. It'll almost never work out that you will get an exact area that will be one of these things there. And there's very few values that are perfectly given in the table. Now the shading is all wrong. It's going off to the right. But the area I'm going to give you, let's call it 25%, would be there. So what could you do? What you could do to make use of the table is you could notice that the rest of this is 75% out here, or 0.75, and this white region does go off to the left. So I can go, and 0.75 means whatever z value I'm looking for is definitely going to be bigger than 0, so it's going to be positive. Let's pop into here then. Let me see if I can find anything close to 0.75 in this table. I know I'm going to have to go to the positive realm. Right here we're stuck in between 2 again. All right, we've got our numbers in here again. Let's see, if I look at this row, we're at the 0.6 row. So we're between 0.67 and 0.68. So what I'm going to do is go 0.675. That's the missing z number. Notice that that makes sense. This number being positive means that you are over 50% of the data, and we can see you're well over 50% of the data. Let me do one more, leaving it to you, and see if you can come up with the answer. So I'm giving you 43% as the shaded region. What is the value of z?